This is the 8th video on electromagnetism for A-level physics. The aim of this video is to investigate the rotating coil and the equation used to calculate the EMF that a rotating coil induces. It's just worth noting that this video covers the rotating coil, which is only explicitly covered in AQA A-level physics. In previous videos we have seen loops moved out of magnetic fields. Coils and bar magnets move relative to each other and magnets rotated next to coils. In all of these situations the flux through the loop or coil changes, and as a result an EMF is induced in the coil. So just jot that down. Moving loops into or out of a field, moving loops and magnets relative to each other, and rotating a magnet near a coil. What all of these have in common is that they change the flux linkage through a loop. All change n phi flux linkage through the loop. Therefore, by Faraday's law, these all induce EMF. They all induce a voltage, so they're all valid ways of creating electricity. Changing the flux through a loop or a coil to induce an EMF is one of the most important ideas in physics. So I'll just note that because we're going to be relying on that idea here. So changing the flux linkage through a loop or coil will induce EMF. Okay, the problem with all of the means we've looked at so far is that they aren't really useful for generating a substantial amount of EMF. They're not viable for large-scale electricity production. To generate a meaningful amount of electricity, we must consider a coil rotating in a uniform magnetic field. This is the rotating coil. So rotating coil in a uniform magnetic field. Okay, to understand this we'll need some pictures. We'll get pictures with a few different perspectives. Here we have a 3D view of a loop inside a uniform magnetic field. The uniform magnetic field is created by the two poles, the two opposing poles. So we've got a north on the left and a south on the right. You might be able to recall from GCSE that if you put these two opposing poles close to each other, they'll make a uniform field in the space in between. Then this rectangular white loop, so if we follow that along, this one here that I'm tracing along in green, that's the loop. Through its center there's a dashed line with some yellow curved arrows going around. This is actually going to rotate. The loop is going to rotate around the axis. We will see this in a different position. It's also going to be useful to look at a 2D perspective. It'll make it easy. We're trying to look at flux changing through this loop. At this point though, we can see that the flux through the loop will be zero, because the field lines will be horizontal and the loop itself is horizontal. The loop would have to be at least a bit vertical to get some of the field lines come through. Now, off to the right of this, we can see the 2D version of this as if we were looking at this end on. You see how the loop there is blue and just appears as a line? Well, that line there, it's as if we were looking just along at this end here. The value of having this picture is that we can see none of the field lines pass through the loop, right? That the nearest field lines pass over the top or underneath it. So there is no flux from this field that passes through the loop. So we'll just note that. The flux is 0, or we can even say the flux linkage is 0 in this case. That applies to both of these. They're just views of the same thing. But when the loop is rotated, we'll see that the flux will change through that loop. So again, we'll look at another 3D picture of the loop and see what we can understand from that. Again, we're looking at another 3D picture, but now the loop, this structure here, is arranged vertically. It used to be horizontal before. If we look back in these two cases, the loop was horizontal, and the loop's just been rotated through 90 degrees, and now the loop is vertical. We can see a difference right away if we consider the field. So the red lines going across horizontally here, they represent the field lines, and they're running from north to south. They're evenly spaced because this is a uniform field. The green dots within the loop, so this collection of them that I've just circled there, they all show the points where the field lines pass through the loop. Well, we've said throughout this series that when field lines pass through a loop, there's flux through a loop. That's what flux is. It's a measure of the number of field lines that pass through a loop. And we've gone from a situation where we had no flux up above, right, in these two cases, left and right at the top. Well, now we've got about as much flux as possible. That loop is in a position to capture a lot of the field lines, have a lot of the field lines pass through. So we've got maximum flux, or so we've got maximum flux or flux linkage n phi. And in fact, when the loop is at 90 degrees to the field, so the loop's vertical and the field lines are horizontal, so they are at 90 degrees to each other, we can say that the flux linkage n phi is equal to n b a, where n is the number of turns in the loop, b is the magnetic field strength, and a is the area of the loop. So the area being all of that space there that's just been shaded in. Okay, it'll also be helpful to look at a 2D version of this as well, just to simplify the picture. Here we have the 2D version of the picture on the left. We can see much more easily now that the red field lines just pass straight through the loop. They're perpendicular to it, so there's definitely flux, and the lines are definitely perpendicular to the loop. Again, the 2D version here is the end-on view, as if we placed an eye at the far end there and looked out along the axis of rotation and just saw the far edge of the loop. We looked at something like this previously. We looked at how the flux linkage through a coil that's rotating, or through a loop that's rotating, changes as the loop is rotated. We've already established an equation for that, so we'll get that equation down and see where we can go with that. The equation for flux linkage through a rotating coil is N BA cos theta, where theta is the angle through which the coil is rotated. So it's sort of like this. If we have field lines coming across horizontally with our loop arranged like that, if the loop rotates some amount, so if the loop rotates itself into that position, theta is the angle it's rotated through away from that normal position, that perpendicular position. That one there, perpendicular. And then we've got rotated. Theta is the angle we go through. If we want to keep generating a voltage, we have to keep changing the magnetic flux linkage through the coil. The only way we can do that is if we keep rotating the coil. And the simplest way to think about that is if the coil rotates at a constant rate, like it has a constant angular speed. In further mechanics, in physics, we write angular speed as omega, and it's equal to theta over t when it's constant. It's the angle we've rotated through, angle rotated, divided by the time it takes to rotate through that angle. So we can rewrite the equation up above as NBA cos omega t. This is helpful because Faraday's law states that the induced EMF is directly proportional to the rate of change of magnetic flux linkage through the coil. Rate of change should sound like differentiation. You wouldn't have to do this in an exam, but it's the best way to make sense of what's going on here. So we can rewrite Faraday's law as a derivative. Faraday's law. The EMF is equal to d n phi dt, the derivative of the flux, right? The derivative of that, the flux linkage, not just the flux. Let's go through and take that derivative. So we know it's going to equal E. When we differentiate NBA, none of that changes. Those are all just constants. The number of loops doesn't change, the field strength or the area of the loop, those don't change. Cos does respond to differentiation. When we differentiate that, we get sine omega t from cos omega t. Also, we have to apply the chain rule, right? We're differentiating with respect to t, so we have to write another omega out like that. So we'll tidy this up. We'll write minus omega NBA sine of omega t. Then we actually drop the minus sign. It's really because something called Lenz's law brings in another minus sign, and the two of them cancel each other out. We essentially haven't been working with the full equation. We've been dropping a minus sign prior to this, and we're introducing it now to get rid of the minus sign right there. And this is the equation that determines the EMF induced by a rotating coil. One final note on this equation. It can be found in the formula sheet for AQA, so you won't have to memorize this equation. Okay, that's that.